In the previous segment, we mainly discussed about like different. We first discussed about the multi-layer perceptron, and then we talked about why do we need better computer system for this machine learning application. Specifically, we told that we saw that the hardware floating point operation like changed or improved a lot in the past 25 years, but then the memory bandwidth or the interconnect bandwidth has not improved as the hardware floating point operation improved. Like the CPUs are better, the computer units are better, but we do not have as good memory or as good interconnect, right. And then we also saw like the scope of accelerators. Today we will see the DNN algorithm, how the DNN algorithm works, and then we will eventually land onto the CNN space. Now, before going deep into the DNN, let us discuss the terminologies we will use. So, remember, we will use these terminologies for like many times, like for the throughout the course we will use these terminologies. Whenever we talk about deep neural network, then we need to know what is neuron. We already discussed what is neuron, like neurons are nothing but they take bunch of input and then they have the weights, the inputs get multiplied with the weights and to produce the output. So, this particular figure is showing generic multi-layer perceptron where we have input layer and then the hidden layer and then the output layer, right. Now, between there are multiple neurons in each of the layers. Now, those neurons in different layers are connected with weights, correct. Again, I am talking about weights, but then in many of the places or in many of the literature you will see that they are called synapses, right. These input layers, the neurons in different layers are connected with synapses, right. Now, each synapse has a weight for the neuron activation. So, as if you remember when we discussed about multi-layer perceptron, we already explained this. Let us say we have 3 neurons in the input layer and 4 neurons in this hidden layer, then we will have total 12 weights between all the neurons in the input layers and all the neurons in the hidden layer, right. Now, this connection between two different neuron in two different layer is nothing but the synapses which has the weights. Whenever we have weights, then the output neuron is computed as the activation of multiplication of all the weights with the input neuron values, right. In this case, we will have summation of I equals to 1 to 3 wij multiplied by xi, that will provide the output, not just that product and then sum, but we have to apply the activation function. So, that is how each of the neuron in each of the layer is getting computed, right. Now, there are some cases where we will see weight sharing, that means multiple synapses use the same weight values. In this case, you can see there are few of the synapses which has the exact same weight value, those are some different type of neural network. Then whenever we say layer is nothing but group of synapses. So, in this particular case you can see that we have this layer 1 and this layer 1 has some input neurons and output neurons. We call these neurons as the L1 neuron inputs, right. It can be image pixel. So, let us say we provide an image to the neural network, then these L1 neuron inputs can be the image pixel, right. And then we have this layer 1. So, after this layer 1 we will have this L1 neuron outputs. We know these output as, or we typically call these output as activations, right. So, these are the common DNN terminology which are being used. We will use this terminology again and again for the entire course, right. Now, similarly, like if we have layer 2, then these particular neurons are called L2 input activations and then these particular neurons are called L2 output activations. Okay. Now, let us see some more terminology. So, there are something called fully connected neural network. So, when we have fully connected neural network, that means all input neurons are connected to all the output neurons. So, in this particular case you can see that all the neurons in this input layer is actually connected to all the inputs in the hidden layer. So, that means this is fully connected, but if you see this particular group of neurons where we have these output layers, there are some neurons in the output layer, but not all the neurons in the hidden layer is actually connected to the output layer, right. So, that is why we call it sparsely connected layer. So, we can have fully connected layers and then we can have sparsely connected layers. When we will discuss the topic of pruning and quantization, we will see that the primary motivation behind pruning is to make fully connected layer to sparsely connected layer, right. There are another kind of deep neural network where we have this feedback connection. So, usually there is one algorithm called LSTM, long short term memory. In that case we have this feedback connection. The usual connections are called feed forward connections. So, whenever we come across this terminology called feed forward network, the feed forward network is nothing but we have bunch of neurons and all the neurons are connected to all other neurons through the synapses or through the weights. So, that is a feed forward connection. Okay. Now, again, as I was saying, there are different types of DNNs where we have fully connected neural network. They are like feed forward network and they are actually known as multi-layer perceptron. We already saw what is multi-layer perceptron and how they actually work, right. Then we have convolutional neural network where we will see that they are feed forward only and then they are sparsely connected with weight sharing. We will soon see how convolutional neural network work. Then there is something called recurrent neural network where we have the feedback kind of connection, which I was showing in the previous slide, and then we have something called long short term memory where we have feedback connection. On top of that there is something called storage, right, because there is some memory involved, correct. So, these are the typical list of DNNs, but we will mainly talk about this fully connected neural network and then convolutional neural network in our course. Now, whenever we talk about machine learning algorithm, there are two phases. One is inference and another is training, right. Now, remember, let us say you are using ChatGPT. So, whenever you are using ChatGPT, let us say you got an assignment and then you do not want to solve the assignment by yourself, you put the whole assignment in the ChatGPT prompt and then you are expecting the solution, right. So, that phase is called inference. That means the ChatGPT algorithm has some weights. So, let us say it has some feed forward network. So, in the feed forward network it has all the synapses, right. So, all those weights are already been trained, right. Now, we are using those trained weights to predict, correct. So, that this phase is called inference, but remember we have to train the weights, correct. Now, that phase is called training. Training is mainly to determine the weights, like what should be the value of the weights. There are different kinds of training: supervised, semi supervised, unsupervised, self supervised, reinforcement, etc. We already discussed about supervised and unsupervised. There are other techniques, as I am saying, that like semi supervised or self supervised. Again, we will not go into the details because they are not exactly in the scope of the course, but just this is for your information that there are different kind of training, right. Now, if we actually perform the DNN training, now let me take a step back and tell you how exactly this DNN training happens. So, whenever let us say we have a multi-layer perceptron which needs to be trained on some data. Whenever we say data, that means we have some features and then there are some labels, right, that constitutes the data, right. Now, let us say we have one multi-layer perceptron which needs to be trained or whose weights to be computed through training from the data set, correct. Now, what happens? So, whenever let us say we construct the multi-layer perceptron, then initially all the weights will be initialized with some random value, right, because they are not trained, correct. Now, with that randomly initialized multi-layer perceptron, if we perform an inference with that data set, then most likely most of the results will be wrong, right. Most of the outputs will be wrong, because our weights are not trained, weights are initialized randomly, correct. Now during training we first initialize the multilayer perceptron with random weights, and then we perform the inference. Then we will see that whatever output we are getting is actually incorrect, right. But we know the correct output, because we already have the data set, in the data set we have the label. So, we know the correct output, right. Now, whenever we have the incorrect output, then we see what is the error. Now, whenever we are talking about this output and everything, so remember everything is number, at the end of the day everything is number, nothing more than that. Okay. So, we have the incorrect output because all the weights in the multilayer perceptron were actually initialized randomly. Then we know the correct output of the labels. From that we can actually compute the errors. Now from the error we need to know like how much these weights should be changed so that the error is minimized, right. Now this is the process of the DNN training. Now what happens, we compute the error. So error will be computed in the very last layer of the multilayer perceptron. Then we will see the gradient of the weights which should minimize the error. Now we will first change the gradient, or we will first modify the weights of the very last layer, and then we will modify the weights of the second last layer, and so on and so forth. So this is called back propagation. Like we computed the error in the very last layer, and then we are back propagating the error, correct. Now in that process of back propagation, as I was saying, that we are computing the gradients, right, gradients of weights which should minimize the error, right. Now whenever we say gradients, that means we are computing some derivatives, correct. Now there are some partial derivative which share computations. There are common terms for every neuron in each layer, right. Not only that, these partial derivatives need the intermediate values obtained during the forward propagation. So remember we perform that forward pass or the inference with the like randomly initialized multilayer perceptron, right. In that case we generated some activations, all the neurons generated some values, correct. So during the back propagation, whenever we are performing the partial derivative, we need those intermediate values obtained during the forward propagation. We can reuse the activation, right. Either we can recompute or we can reuse the activation, because I mean during the forward pass anyway we generated the activations, right. So why not to reuse. So these are the key observation in DNN training. Whenever we will discuss the DNN training or the algorithms for DNN training, or rather I should say hardware efficient algorithms of DNN training, we will discuss these things in more detail. Now whenever we perform this DNN training, there is one very common problem which is known as vanishing gradient. You might have heard of this problem. So let me take some time to explain what is vanishing gradient. As I was saying that we compute the error, and then based on the error we actually compute the gradient and all those things. So there are specific algorithms which compute the gradient, or which tries to minimize the error with respect to the weights. So gradient descent is one of the popular algorithm, but instead of gradient descent, stochastic gradient descent is used to update the weights for faster convergence, right. Now SGD works well for just a few layers of neural network. Now remember I was saying that during training we have something called back propagation. Now as this back propagation continues into many layers, the gradient multiplied with weight. So remember whenever we are doing the back propagation, so we are multiplying the gradient with respect to we are multiplying the gradient with some weights, and usually these numbers are less than 1, right. So or very small values, they are like very small values. Now imagine you have like let us say 10 layers of multilayer perceptron, and during training you are actually multiplying let us say 10 numbers where all the numbers are less than 1. So you can see I mean why we need to multiply 10 numbers, because you are doing that back propagation. So whenever we reach the very first layer, the amount of the change of the weight will actually depend on all the other layers, correct. So that gradient, whenever we are computing the gradient of the weights of the very first layer, that might be computed by multiplying all the 10 numbers, or all the 10 numbers which are less than 1, right. Now imagine you are actually multiplying 10 numbers less than 1 to, which is basically nothing but the update in the weight for the very first layer. So that weights are usually, that update of the very first layer will be very small, right. That means the gradient is actually vanishing when we are reaching the initial layer. So this problem is known as vanishing gradient problem, which is like very common problem in any ML training. There are so many literature, there are so many work which get proposed or which are proposed just to address this vanishing gradient problem. We will see some of the solution. One of the solution is residual connection. We will discuss like what are the residual connection, what are the hardware implication and all those things. There are specific activation function which actually helps to solve this vanishing gradient problem. For example, rectified linear unit instead of sigmoid can be used so that the range of value is less. Batch normalization is used to solve the vanishing gradient problem. Again, this is not a ML course, so we will not deep dive into this vanishing gradient, the mathematics of vanishing gradient and all those things, but I just want to let you know that since vanishing gradient is there, we have different types of neural network. Like this residual connection is specifically for vanishing gradient. Since we have residual connection, that again adds to computing, so that adds to the challenges in computing. Okay. Now let us move on. As I was saying that what is the relevance of computer hardware, right. Remember the course is on computer system for machine learning, correct. So remember, whenever I was saying that the back propagation is happening, during back propagation we need to know, or we need to use the activation which are actually used in the forward pass, right, or during the inference with that randomly generated weights or maybe partially trained model, right. So one way to minimize the computation is caching. Like we can say that we can store all the values or all the activations which were used in the forward pass, and then we can reuse during the back propagation. So we can cache the values, we can store the values, right. So identical computations can be reused. We will actually eventually see many hardware ML accelerators exploit these properties. They like curated, those hardware accelerators are very much curated to the algorithm, and it carefully analyze like how the algorithm is getting executed, how we can use or how effectively we can use caching, which exact data will be reused and all those things. Then let us now talk about convolutional neural network. So remember we talked about this multi-layer perceptron, right. These multi-layer perceptrons are nothing but, like let us say those are nothing but the deep neural network. So remember in the multi-layer perceptron we are providing multiple images, multiple inputs. In the very first input layer there were multiple inputs, correct. Now this convolutional neural network came into the picture mainly for image recognition. Let us say you have an image of an animal, the task is to recognize whether the image is of cat or dog, right. Now if we provide or if we pass that image onto a multi-layer perceptron, then it will treat each pixel in that image as input to a separate neuron, right. Because I mean whenever we have image and that needs to be recognized, then those image pixels are the features. So those image pixels will be going to the input of the multi-layer perceptron, right. That is how multi-layer perceptron works. But then remember, as a human being, whenever we have to identify or whenever we have to recognize some image, we do not see those pixels individually, correct. We try to capture the spatial similarity on the image I think there is some typo which I can fix later. We try to like capture the spatial similarity on the image pixels, spatial similarity present in the image pixels, right, because again neighboring image pixels are similar and eventually they form the entire image, correct. So, if we use multilayer perceptron, it misses the spatial similarity in the image, correct. That is why not we should capture information from the neighboring pixel. So, instead of just providing the input as individual image pixel, we should capture the patches. We should see one patch of the image and then analyze, then we should go to the next patch of the image and then analyze. That is how we can capture information from the neighborhood pixel. So, patch is nothing but one cluster or one segment of the image, right. If we analyze a different segment of the image, then we are actually analyzing the neighborhood pixels, right, but with respect to one particular pixel. And to do that, we have something called convolution. Now, in this convolution operation, we actually slide, we will again see in more detail, but at a very high level, we slide a small matrix of parameters which are known as filters across the input image, and those filters are actually trained through backpropagation. So, again at a very high level, if we want to perform image recognition or if we want to apply any machine learning algorithm on the image, and then let us say if we just have multi-layer perceptron, then we will provide each of those pixel as the input of the multi-layer perceptron, correct. But as a human being, that is not how we analyze an image. We analyze an image as like patch by patch, right, because we see what is the neighborhood pixels and all those things, and that eventually forms the entire image, right. So, in convolution operation, it actually helps to capture the information from the neighborhood pixel, right. In convolution operation, we slide a small matrix of parameters which is known as filters across the image, and these filters are trainable weights. So, they are trained using backpropagation. Now, we will slowly start discussing about CNNs, convolutional neural network. Specifically, we will discuss about deep CNN. There are like very well known fight where the fight is about how deep is deep. So, typically if it is like more than 5 layers, then we will say it as deep convolutional neural network or deep neural network. So, nowadays if you talk about deep neural network, people understand it as convolutional neural network, because usually multi-layer perceptrons are not used in like large scale applications. So, this particular pipeline or this particular figure is showing the usual layers or usual notion of deep CNN. So, we provide the image as the input to the convolutional layer. Now, usually the convolutional neural network convolutional layers try to capture the features. Okay. So, whenever we say features, that means let us say the image is of a human image, right. Now, how to capture, how to know that the image is of a human image? It will detect nose, ears, etc., right. So, initially the initial layers, there are, as I was saying, that there are multiple layers, like multiple convolutional layers. The initial layers capture the low level features like the edges or the brightness, intensity of the pixel, something like that, right. And the later layer capture high level features like, as I was saying, nose, eyes, ears, and then there are fully connected layers. After that, it says that whether the image is of human being or cat or dog, something. So, I mean once we have these high level features, then this CNN can say that okay, if there are like eyes, nose, and which are they are in this kind of position, then we can categorize it as human being or some animal, right. So, usually there are like these convolutional layers, and then there are 1 to 3 layers of fully connected layers. Again, fully connected layers are nothing but those multi-layer perceptron. After that, we will get the classes. Classes are nothing but, I mean, let us say we have this convolutional neural network which classify the image as like multiple animals like maybe cats, dog, horse, cow, etc. So, those are different classes which will be the output of convolutional neural network. Now, whenever we talk about convolutional layer, yes, it has convolution operation followed by activation. Okay. So, without any activation there will not be multiple layers. If we do not have this nonlinear activation, then all those convolutional layers can be fused to form one particular layer. So, that is why each of the convolutional layer or each of the conv layer is followed by a nonlinear activation. Okay. Now, similarly, the fully connected layer, we already discussed about fully connected layer where all the neurons in the previous layer is connected with all the neurons in the next layer, and all those connections are nothing but synapses or the weights. So, those are called fully connected layers. Whenever we say fully connected layers, yes, it has fully connected component followed by activation. So, remember, between each of the layer or between any two layer of CNN there is nonlinear activation. Okay. Without nonlinear activation we can collapse the whole CNN to one layer. Okay. Now, again, I mean, there are more components between convolutional layer. There are something called normalization. We will see, do not worry, we will see what is convolution, how exactly it works. We will also see how actually normalization works. So, apart from normalization there is something called pooling. So, this normalization is actually used to make sure that the numbers which are getting the range of those activations are not very high. Then pooling is also used so that it like to incorporate like variances. So, let us say if one image of one, let us say some art piece is rotated, or let us say one image of art piece is actually translated, then it still should be classified as the same image. So, pooling ensures that there is no, I mean, the translational variance is captured. We will see what are the computation which is being used in pooling, in normalization, or at a very high level, like what are the computation which is being done in convolution layers, fully connected layers, etc. So, that is the end of this segment. So far we have seen how the DNN or different terminologies of deep neural network, and then we saw how the different layers of this convolutional neural network form. In the next segment we will deep dive into convolutional layer. We will see how exactly the computations happen, and then of course, we will also talk about this normalization, pooling, etc. Thank you for your patience. Thank you for listening. Yeah, we will go to the next segment. Thank you.